It's 1:02, so I guess let's get started. We're absolutely delighted to have Yuliy Sannikov here among us today to give the first keynote lecture of the Brazilian Econometric Society meeting this year. As a representative of the society and also at a personal level, I am honored to have the opportunity to say a few words about Yuliy's work by way of introduction. Well, to put it very simply, Yuliy's work in dynamic game theory and dynamic contracting is widely recognized as the single most significant breakthrough in economic theory in decades. But perhaps more importantly, the impact of Yuliy's methodological innovation transcends the field of economic theory and reaches the realm of various applied fields. For example, his dynamic agency papers with Peter DeMarzo have become classics in corporate finance and have shaped the way contemporary researchers think about capital structure, firm dynamics, and managerial compensation. His work with Marcus Brunnermeier has developed a new paradigm for examining the role of financial frictions in macroeconomics. It is quite safe to say that it is precisely this unique combination of Yuliy's powerful and very general methodological innovation, together with the new insights that it brings into various applied questions, that makes Yuliy's work so special. So it wasn't a surprise to anyone when 4 years ago, Yuliy was awarded the prestigious Bates-Clark Medal by the American Economic Association. I witnessed firsthand the impact that Yuliy's work had in the profession, beginning with the theory community. I met Yuliy back in 2004 or 2005 when he was on the job market and I was a graduate student at Penn. We started collaborating a few months later. Yuliy was basically on his job market tour, showing the theory community his new paradigm for modeling and studying dynamic games subject to moral hazard. His model was one of a repeated game played in continuous time, where the observations of the player's actions were distorted by a Brownian motion. In that quite revolutionary paper, which got published at Econometria a few years later, Yuliy showed us how to use stochastic calculus and martingale arguments to connect the law of motions of the player's continuation values and their incentives. With that kind of apparatus in place, Yuliy goes on to develop a characterization of the full set of equilibrium payoffs and behavior by a relatively simple analytical object, an ordinary differential equation. Sannikov's optimality equation is truly a piece of art. It shows in a very clean manner how the trade-off between efficiency and incentives is resolved in games with moral hazard. And the resolution of this trade-off is as beautiful as it is intuitive. It depends on the Gaussian curvature of the set of equilibrium payoffs. As we expect, in order to provide incentives for players to cooperate, their continuation payoffs must be sensitive to the noisy public signals about actions. This noisy dynamics leads to a very familiar inefficiency. The convexity of the set of equilibrium payoffs implies that this inevitable exposure to risk will hurt the common interest of the players. While we expect some measure of convexity to play a role in the resolution of this trade-off, in discrete time, it's simply impossible to make a precise connection between the geometry of the equilibrium set and the efficiency cost of incentives. The beauty of Yuliy's work is that it makes this connection precise and exact. Thus, we can view the continuous time model as a useful approximation, which helps us get a better understanding of incentives in dynamic environments. Well, I could go on and on and on. Yuliy has at least another handful of papers with profound insights. And I could also talk forever about how great a co-author he is. And I know a few of his students too, so I could talk about how splendid a PhD advisor he is. But you're not here to listen to me. So in the interest of time, I'm going to stop. Without further ado, I introduce you to our keynote speaker, Yuliy Sannikov. Yuliy, please, the stage is all yours.
Okay, thank you, Eduardo, for this great introduction. I really didn't expect that. I was just thinking myself. Okay, I was just thinking about how, over the years, it's been a real pleasure working with Eduardo on our joint papers. Um, so thank you very much for having me. So I would like to talk today about a paper I'm working on with a colleague at Stanford, Andy Skrapach. It's called Dynamic Trading, Price Inertia, and Front Running. So in this paper, we want to model, we want to think about a model of a market, for example, people meeting together in the stock market and trading dynamically. So they have some motivation for trade. It could be hedging, diversification, or they could have, some portfolio rebalancing, some fundamental information. So they want to buy and sell and trade with each other. And we want to think about the dynamics in this type of a market. So get realistic processes for prices, understand the price impact that traders have, and overall model the market together. And the motivation for modeling market as a whole is recently there has been a lot of interest, a lot of recent developments. So one of the things that has happened recently is that in the US, retail brokerages such as Ameritrade, they suddenly started, they dropped their fees for execution of transactions. So you can now trade stocks and you do not have to pay anything per trade. And this is supported by something called payment for order flow. So it turns out that these brokerages, they could sell the flow of retail investors to institutions and get paid just from directing this flow, because somehow it turns out that trading against retail flow is a lot more profitable than trading against institutional flow. And why this is the case? Well, it's important to understand some properties of trading in the market as a whole and some heterogeneity in order to understand why this is the case. So another reason to look at the market as a whole is there's been some interest in high frequency trading. So there's been some interest in dark pools. And this paper is not meant to address any one of the questions in particular, but just to introduce a broad model of trading in the market. And what I want to start with, to put things into perspective, to mention this classic paper from Financial Mathematics by Amgren and Chris, which is a very nice problem of a single trader. And the question is, well, how to trade optimally given a realistic assumption about price impact that trades would have. So in this paper, there is a trader who has some, who wants to do some transactions. So he wants to sell, let's say, a large block of stock of a size X0, and the goal is to sell this entire block over time period 0 to capital T. And the trades, they have a price impact. And there are two types of price impact. There's instantaneous and permanent price impact, and these are basically motivated empirically. So that's why they made this assumption. It's a nice, clean assumption that's empirically motivated. So Instantaneous impact is that the price is going to instantaneously react to the speed of a trade, to the selling rate Q. And permanent impact is that the price is going to change as a result of the total quantity sold from the beginning of sales until the current time. And the question is, well, what's the best way to trade this block? The objective function here is the trader cares about the expected revenue. So he wants to try to get a better price for the shares that he sells. And the trader also doesn't like the variance of revenue. So the trader ideally would like to sell at the price which exists in the market right now, but because he has to spread out the trades over time to minimize price impact, the price at which the whole order executes, the average price, is going to depend on the market volatility, and because of risk aversion, the trader doesn't like it. So there is a penalty for the variance of execution price, and this is a problem. One thing I want to say is that this objective function, it turns out to be in the setting equivalent to having quadratic holding costs. So the trader is penalized for the integral of holdings which are still remaining at each moment of time squared. And why this is quadratic holding costs? It's because the longer you hold the shares and the more shares you end up holding, the higher is going to be the variance of the price because of volatility at which you finally end up executing. Okay, so those two things are equivalent in the setting. Now what we want to do is we want to basically put together many traders like that in the market. And instead of assuming that price impact and price is exogenous, we want to derive how prices move, and we want to derive what the price impacts are from the behavior of people in the market. Okay. In our setting, here there's equivalence between quadratic holding costs and these mean variance preferences. And in our setting, quadratic holding costs are actually going to be more convenient because with quadratic holding costs, so here the trader has a fixed quantity that he wants to trade, but with the quadratic holding costs, how much you end up selling could depend on the price. So if the price drops, you may want to sell less. If the price goes up, then you may want to sell more at a higher price. So we need this type of a flexibility. So let me. So this is the financial mathematics classic paper, and we want to build upon this idea and create a whole market of traders like that interact. This is what we want to do. Let me just mention some papers in economics that look at the whole market. So obviously, so here's a limited slide with some limited literature. So obviously there are the papers on noise trading. So there are Kyle model, Beck model, there's an insider, and who has some information and has the motivation for trade. Then there are some arbitrageurs, and then there are some noise traders. Okay, so so this is one model of trade, and we want to build a model in which in which every single trader is rational. So if there are traders that look like noise traders, they still are market participants that try to trade rationally. So there are models of rational trading in which people have some motivation for trade which are symmetric. So there are symmetric markets, and there's a very nice paper by Vayanos, and there are some more recent papers by Du and Zhu. In our paper, we are particularly interested in heterogeneity in the market, the fact that there are some larger traders and then there are some smaller traders, in order to be able to apply the model to recent developments, for example, phenomena such as payment for order flow. There are some challenges to having a dynamic model of market, which is asymmetric. But there are some very nice papers, for example, Malamud and Rostek, of one-shot models where traders are asymmetric, and a lot of the insights that they get in the one-shot model also translate into our dynamic model. And so, of course, I cannot proceed without mentioning some popular press and some the book by Michael Lewis, Flash Boys book, Dark Pools. So there is a lot of interest in this because of the rise of high-frequency trading. Okay, so now let me go to tell you what we do, and the big picture is that we want to think about Amgren and Chris, a single trader problem, as a starting point, but we want to put many of these traders into a market. Okay, and in order to put them into a market, we need to add several layers to Amgren and Chris. So the first layer is still this individual optimization problem, but we have to generalize it, because in Amgren and Chris, it's a specific assumption about price impact, but we have to allow for more general types of price impact, and it will turn out that the generality that we have is actually empirically relevant. So we have to first look at a more general version of an individual trader's problem. One of the ways how we have to generalize Amgren and Chris is we have to include the possibility of price momentum, so price inertia. So why is that the case? Is because in Amgren and Chris, prices are martingales in the absence of trades by the trader, but when many traders interact, then they're going to push the prices, and the prices, they will have some momentum. So that's important to include. So that's one, individual optimality. Two is when we put many traders together into a market, then we want to derive how prices are going to behave as a result of the strategies of individual traders. So the second step is to put traders in the market and to impose market clearing to derive the price. And then the last thing is that we have to close everything, and we have to impose the consistency requirement. So instead of assuming price impacts of traders exogenously, we have to realize that these price impacts, they come from the willingness of other traders to accept the flow of a given trader in the market. Okay, so if a particular trader trades, he's going to push the price, for example, selling to push the price down. And as the price drops, the asset gets cheaper. It will become more attractive for others to buy it, and in order to encourage the other traders to buy the asset, the price has to be pushed down sufficiently, and this is going to be the source of the origin of the price impact. So this has to be endogenized. So These are the 3 layers. And it will turn out that every single one of them is a nice problem in of itself. So the first one is a nice problem because it's a generalization of the classic Almgren and Chris problem. So let me talk about each one of them one at a time, starting from individual optimality. So so here's a generalization of Almgren and Chris. So a trader has some inventory, okay? And the motivation for trade is that, so this inventory, these could be brokers that, for example, get some orders from their clients and execute these orders on the client's behalf. This could be an institutional investor that has to do a periodic portfolio rebalancing or track some index. So there could be various motivations for why these people have to trade. Okay, we call the excess shares that need to be bought or sold inventory of a trader. Okay, so inventory doesn't mean the total number of shares in the portfolio, but this is how much excess shares the trader has to buy or sell. So there are some shocks to inventory, and they're in the form of a martingale. So equally likely the trader is going to get new shares to sell as the same number of shares to buy. And then the inventory changes because of the actual trades, the actual sales. So Q are sales, and if Q is negative, the trader is buying shares. So the trader's payoff is the trader is going to have quadratic costs in holding inventory, holding excess inventory. So it could be motivated, for example, by risk aversion. And there's a coefficient BI on the cost of holding inventory. And we can think about BI as this is whether it's a large investor that can hold large amounts of inventory and patiently wait for a better price, or if it's a smaller investor who wants more immediate execution. So the price, this is a generalization of Almgren and Chris. There is some baseline price. And trades, they push the price by a price impact function F. So F could have an instantaneous impact term, permanent impact term, and some transitory term. So, in fact, it's an empirical fact that there's also not just permanent and instantaneous impact of trades, but there's also some transitory impact that that decays, over time. Okay, so this is individual's problem, and here the price follows some stochastic law of motion, and in order to solve this problem, I'm going to start with an important observation that here, even though the price is stochastic, the optimal strategy, how much to sell, depends only on the expectation of a future price path. So expectation of future price path is important because when prices have momentum, if prices go up, then you want to wait to sell a little bit later. And if prices go down, you want to try to sell faster while the price is still high. Okay, so the expectation matters. But because of this quadratic holding cost, it turns out that only the expectation matters and the variance of price, for example, does not matter. So the first fact is that for solving the individual problem, if we imagine that prices are deterministic, then the solution is going to be exactly the same. And if the prices actually are stochastic, then every single time there's a surprise to the expected future price path that's going to have an additive impact on on optimal selling. So this is super because it's much easier to think about deterministic paths rather than stochastic paths. So then the second thing is before going into a little bit of math, there's going to be some, but not a whole lot. I want to give a little bit of intuition about the trader's problem. And then there are two aspects that that are here. One is that of price impact. So with price impact, there is a trade-off that if the seller sells slowly, the seller is going to get a better price on average, because selling slowly is going to reduce the price impact. And if the seller sells slowly, then the price is going to, in expectation, basically gradually drift downwards. Okay, and if the seller is choosing to sell fast instead, at a faster rate, then the price is going to overshoot. The seller is going to get a lower revenue, but of course, the faster execution has the benefit that the seller is going to have a lower holding cost. So price impact is what Amgen and Chris is about, except that, of course, here, the price impact is of more general form. And then the second aspect of a trader's problem is that there is price momentum. So in Amgen and Chris, if the trader doesn't trade, then price is a martingale. But here, we have to allow for price momentum. Because we will see that once we put many traders into the market, the price will have momentum because the price will be pushed by the interaction between the traders. And of course, with price momentum, it's very simple intuition. It's buy low, sell high, right? If the price is going down, then it's better to sell sooner while the price is high. That's how it's going to impact the traders' incentives. And if the price is going up, then it's better to wait and to sell a little bit later. So this is how price momentum intuitively is going to enter sellers' incentives. So, so now how to trade optimally? There are two ways to pose the question. So the equation for the price, how trades affect the price, there are two p's in this equation. One of them is p hat, what the price is going to be in the absence of trades, and p, which is the actual price impacted by the trades. And one way to pose the question is to ask, well, given p hat and given the initial inventory, what is the optimal trading path Q? So this is the way that Amgen and Chris pose the question. Another way to pose the question is, well, it's actually equivalent, but given P and given inventory, what is the trading path which is consistent with optimality? Okay, so these are very related questions. Essentially, it's, you know, an answer to one question immediately gives the answer to the other question. And Amgen and Chris answer question one. But it turns out that it's easier to answer question two, and it's also more useful for our purposes to answer question two. Why? Because when we put these traders together in the market, P, the actual price is going to be the same for everybody. This is the actual price that an empiricist observes, that you observe in the stock market. but P hat, they're going to be different for different traders, because what the price would have been if a particular trader did not trade, well, that's different for the different traders, right? So once we put the traders together and talk about market clearing and answer to question 2 is going to be more useful for us. But I want to highlight this difference, this distinction between one way of posing the question and another way of posing the question in order to avoid the confusion. So, okay. So the question is optimal pairs of the price path and the selling path, how much the trader is trading inventory. And so this is the question. So what are the incentives of the trader? So so here it's useful to write down the first order condition for the trader in order to break down the incentives. So what is the impact on utility of selling an extra share at a particular time t? So there are several impacts. So the first one is, of course, when the seller sells the share, then it's going to generate some revenue. So the seller is selling at price P, that's going to generate revenue P. That's the first impact on utility. The second impact is through the price impact, through the impact of this transaction on future prices. And that affects the trader's utility to the extent that the trader will have to be trading later. So if it's a small trader that just has this one share to sell, then the small trader would not care about the impact on future price because he's not going to be trading later. But if it's a large institutional trader that is selling continuously, some large block of shares, then we have to take into account the impact of a particular transaction on the price at which further transactions take place. So this is the reduced revenue from future sales impact. And then the third term in this first order condition is the impact of sales on the fact that once you sell this share, if you have a certain number of shares to sell, you're going to have a lower holding cost. Okay, so that's the first order condition, right? And now we can apply this first order condition to look at some optimal paths of P and Q. And the first natural thing to look at, of course, are exponential paths. So these are paths where the trader is trading this block exponentially. So the selling rate is proportionate to some coefficient kappa times the number of shares. And the bigger the kappa, the faster the trader will sell this whole block. And we want to ask the question, well, in order for the speed of trade to be optimal for the trader, what does the price have to be? Okay. And we can derive this price path. It's also going to be an exponential price path, exponentially converging to some long-term level from the first order condition. Okay, so if you plug in exponentially decaying inventory and exponentially decaying selling rate into the first order condition, and if the price is converging exponentially, then we can basically derive what that price has to be. And this price has to be equal to the pi function times the inventory, where a pi function depends on the price impact function f. Okay. So let's take a look at this function, this pi function. So pi function, it turns out, is going to be an increasing function. And why it will be an increasing function? Well, it turns out that if pi is not an increasing function for some price impact f, it turns out that f is not a very good price impact to assume, because this price impact would allow the seller to get infinite utility by some crazy strategy, like pump and dump strategy, where the seller is pumping the price by buying and then trying to sell at the high price. So there are these not all price impact functions are should be allowed, right? And for any price impact function which is allowable, pi turns out to be an increasing function. Okay, so here's a graph of a typical function pi. So we see that pi of 0, we can calculate directly, what it has to be. It's minus bi divided by r, and then it crosses 0 somewhere. It's an increasing function. The slope at which it increases asymptotically turns out to depend on the instantaneous price impact. So pi summarizes the essential properties of this price impact function f. And pi tells us where the price should start, and in order to give the trader incentives to trade at a particular rate kappa. So let's think about, intuitively, fast rate versus slow rate. So a trader that's trading fast at a fast rate kappa is actually generating a large price impact. And this trader can reduce price impact significantly and get a much better, try to get much better revenue by lowering kappa, by trading slower. So what would give a trader incentives to trade at this very high rate and generate very high price impact? Well, that will only be the case if, in fact, the price has a very strong downward momentum. So somebody will have incentives to sell very, very quickly if he sees that the price is dropping very fast in the market naturally. So that will, give this trader incentives to even though sales generate have a high price impact, to basically try to sell very, very quickly, to sell at the high price before the price goes down. So that's why for very large kappa, function pi has large values. And for very low kappa, the trader will have incentives to delay instead of selling fast. If by delaying you can get a much better price if the price starts low and drifts up. So for kappa close to 0, pi is going to be negative. Okay, and of course function pi intersects 0 somewhere, which corresponds to price which is a martingale. So a trader, if the price is a martingale, consistent with optimality is some trading rate kappa hat. And of course, kappa hat depends on the price impact of the trader. Somebody who has larger price impact is going to have a larger function pi, is going to have a lower kappa hat, lower natural selling rate. Okay, so for exponential price path, this is a characterization of optimal trading of a trader. Now, let's put this together. So suppose that the price now is a mix of exponentials. So in that case, consistent with the mix of exponentials, what is the what are the inventories that are what is the path of inventory which is consistent with optimality for that price? Okay, is that, well, of course we have to take this price and term by term, the inventory is going to be additive in each component of the price path. So we are going to have a sum of different terms here, and we are going to have an extra term which corresponds to the natural selling rate of kappa hat, right? Because kappa hat corresponds to basically a price which is a martingale. So so it's as if there is a missing term in this equation, and this missing term is going to have this extra one, right? And now, given this expression, given the price path, and given the initial inventory, we can pin down this missing constant, and we can answer the question. We can answer the following question. Suppose that suppose an empiricist observes the actual market price, the actual path, and observes how much inventory the trader has, and wants to infer how much this trader will want to trade at this observed price. So in that case, we can we get the expression for how much this trader is supposed to trade, you know, basically from the result from the previous slide. So this is an important point, and let me summarize it in a proposition. So proposition A is a generalization of Elmgren and Chris to price momentum and to general form of price impact. And proposition A says that for a price path, which is a mix of exponentials, so it could have, of course, one of the kappas could be 0, right? So that's going to be the long-term price to which PT is going to converge. And for some initial inventory, there's a unique trading path for the seller to trade this inventory if P is the actual price that's observed in the market, and we have an expression for this what is the optimal trading path of this trader from which the trader would not want to deviate given price PT. Okay, so that's the result, which is characterizing optimal trading with price momentum and with general price impact. And if you look at this expression for Q, how much the trader is supposed to be selling, let's get some intuition. So there is a kappa hat, which is the natural exponential trading rate. And there is an adjustment for the different terms which take into account the different types of momentum that the price has. So in the absence of price momentum, it's optimal to sell at rate kappa hat, which is where pi function intersects the horizontal axis. And then there are different adjustment terms for the price momentum. So obviously when the price is going up, the seller would want to sell a little bit later, and if the price is going down, the seller would want to sell a little bit sooner. So, okay. So now that we have a solution to the problem of an individual trader, and in this problem, we were quite general in our assumption for the price impact. Now we can try to put these traders together in the market and see how they trade and what is going to be the price that is going to clear the market. So market clearing is, now imagine that we have different traders with different holding costs meeting together. Let's assume what their price impacts are. So the price impact, thinking about the future a little bit, we'll have to tie this all in. So we'll have to, each of the price impact of each trader will have to arise from the willingness of others to accept the flow of a given trader. But for now, we take them as exogenously given. And we ask the question, well, for a given vector of inventories, what is going to be the path of price, which will result from trading these inventories, and how much will each trader trade and how fast? Okay. So in order to address this question, let's first consider price paths which follow exponential functions. And ask the question, well, is there a vector of inventories for which this is going to be the price path? Okay, and something that I forgot to mention is that in this talk you'll see, prices which are positive and prices which are negative. And I just want to say that when I say PT, this is not, doesn't really correspond to the actual empirical price in the market, but it's some normalization, price shifted relative to some specific constant level. So negative price doesn't literally mean negative price, but it's the deviation of the actual price from some baseline level. So exponential path of the price literally has to be interpreted as this is the price which is converging in expectation exponentially to some long-term level. So it's a price that has some exponential momentum. So from an earlier result, proposition A, okay, if we have a price path which is just a single exponential, then we know what is the optimal trading path of any trader which is consistent with this price. Okay, and then there are two terms. There is one term which comes from this exponential trading rate, and there is another term which comes from the natural trading rate of the trader kappa hat. Okay, so now markets have to clear, which means that the sum of Qs has to be 0. And in order for the markets to clear, well, we have to match the coefficients on every single exponential in the sum. And if it happens that kappa hat for the different traders are all distinct, so the different traders, they have different price impacts, then the answer to this question is going to be particularly straightforward. And if kappa hats are not distinct, well, there are some details to work out, but the answer is going to be essentially the same. So if kappa hat are all distinct, then in order for the markets to clear at every single moment in time, the coefficient on the individual exponentials which are distinct, they have to be all 0. So yi's have to be 0, and the sum of the inverses of pi I of kappa, they also have to be 0 in order for the coefficient on this exponential kappa that we started with in order for those coefficients to add up to 0 for the markets to clear. Okay, so so this equation that the sum of inverses of pi i's has to equal to 0, that this is a market clearing condition, which is going to narrow down the set of possibilities, kappa, for any market with any set of price impacts. So let's take a look at it in a little bit more detail. So this is actually a part where, when we discovered it, it turned out to be, we felt that this, really mathematically beautiful, and it wasn't like anything we have ever seen before. So that was really cool. So let me talk about how it works. So pi, it's an increasing function, and in kappa, and it means that 1 over pi is going to be a decreasing function, except for one point, kappa hat, where pi intersects 0. 1 over pi is going to go to minus infinity and then going to go to infinity. So on the left graph, left top panel on this slide is pi, right top panel is 1 over pi in this slide. Now, if we add up 1 over pi across all traders, then it's going to be a function which is decreasing, except it's going to go to minus infinity and then come back from infinity n times, once for every single trader. And because it's a monotone function, we can calculate the number of roots that this function is going to have. And each root satisfies a market clearing condition, because the sum of 1 over pi I, so let's take a look at the previous slide, each root corresponds to the possibility of clearing markets. Okay, so each root of this function, sum of 1 over pi I, corresponds to an allocation which is traded exponentially at rate of the appropriate kappa, and markets will clear. So we have n-1 allocations like this. So allocation is basically a vector of inventories. It's another way I call it. And we have n-1 vectors, and they almost span the whole set of inventory allocations. We need just one more vector to add so that the whole set is spanned, and then we will be able to tell for every single allocation vector how trade is going to proceed. And the remaining vector, it turns out, is the efficient allocation. So the efficient allocation is one in which the inventory is allocated in such a way that the marginal holding cost is the same for every single trader, and the marginal holding cost equals the price. So under efficient allocations, players will not want to trade, and this efficient allocation corresponds to trading rate kappa equal to 0. And the efficient allocation vector is, well, it's just it's just this vector for kappa equal to 0. Okay, so every single allocation that we have solved for on this slide is a misallocation, where the sum of inventories adds up to 0. And there's an equal, it's a balanced market in which the buyers and the sellers, they want to trade equal amounts, and at some rate, kappa, they will trade in equilibrium. And in addition, there is this extra efficient allocation where every single trader holds a positive or a negative number of shares that corresponds to their holding cost coefficient, okay, and the efficient allocation, there's going to be a price at which no trader wants to trade. Okay, so if we have n vectors that span the, so in fact we have exactly n vectors that where the markets can clear, that correspond to exponential paths of price, and if we take those n vectors together, we can decompose every single allocation into these vectors, and then we get the result. We get the following result, which is a very, very nice result, that given any price impacts, assume any price impacts of the traders, then for any initial set of inventories, there is a unique path of trade, how traders optimally trade their inventories. There is a unique path of trade, unique path of price, and unique path of selling or buying, such that no player wants to deviate. Okay, so this is a very, very nice result. Okay, and when players trade, then price is going to be a mix of exponentials. It's going to have a constant coefficient which corresponds to the loading and the efficient allocation, and it's going to have a coefficient on every single other exponential component that basically is the speed of trade for each component. Okay, and so you may be wondering, well, wasn't there wasn't there like what did they hide here? Because I did hide something, because here I made the assumption that I looked at prices which are exponential functions, and so basically in this proof I jumped to the conclusion, and I technically only proved that there is a unique price path which is a mix of exponentials, which such that markets will clear. Okay, so in order to make the claim more complete, I actually have to make a statement that not just for a price which is a mix of exponentials, there not only among those prices there is a unique equilibrium, but among the whole set of continuous functions. And technically speaking, in order to make this more general claim, I have to allow for complex kappas, so that the price paths which have this form, and those could be ruled out, because it turns out that if a price has some cycles, then it can never arise in equilibrium, because a price which has cycles is not going to be consistent with optimality for any price impact, because everybody would always want to try to sell when the price is high at the high point of the cycle, and buy at the when the price is at the low end of the cycle. So only exponential paths of price are consistent with market clearing, and no others. Okay, so recap is we have a proposition B, which tells us that for any price impacts that we can assume for the players, so players could, so price impact is actually something that empirically is hard to measure. In order to measure price impact, in order for a particular institutional investor to measure its price impact, this institution has to make experiments by trading different amounts to see how they actually affect the price. So price impact is actually something which is hard to know in practice. So the fact that if we assume that the price impacts are exogenous and the players maybe irrationally believe that these are their price impact, may not be such a far-fetched assumption. But if we assume price impacts as exogenous, then proposition B says that there is a unique map from the set of players' inventories to their rates of trade and to the price, which characterizes optimal trading to efficiency. And when we have inventory shocks, then the way that the inventories evolve is that the inventories, they evolve due to the shocks and due to the trades among the traders. Okay, so so this is proposition B. Okay. And the last thing that I want to do is, of course, we want to think about consistency. So we have assumed some price impacts and we were able to allow for any general price impacts. And ideally what we want is we want to tie everything together. So we want the price impacts to actually correspond to follow from this dynamics. Okay, so what does it mean, consistency? So let me talk about consistency. So the question is, if we have trading dynamics described by Q, which maps inventories to trades, and P, which maps inventories to the price, then what does it imply about the price impact of a given trader? And here, essentially, we are asking the question, well, given the strategies of all other traders, how much should an individual trader have to push the price in order to get them to accept a certain flow? Okay, and so what is the correspondence between the flow of an individual trader and the change in the price that's necessary to accept, for the others to accept this flow? Okay, so here, in order to derive the price impact given Q and P, here's an observation. So the trader's inventory is actually the trader's private information. Okay, and the trader could trade optimally, or the trader could deviate. So the trader could choose any other path of trade, which would correspond to optimal trading for some other inventory X hat. Okay, so effectively the trader can pretend to be another type, a type with different inventory, and trade differently. And this is going to result in so when the player is pretending to be another type, then all other traders are still trading according to their types, but this particular trader is pretending to be somebody else. So this is going to result in a different price path. We can compute what this is going to be, and this is going to result in a different path, how the shares are reallocated among the traders. Okay. And we see that the trader I, in the whole vector, he has basically 1 degree of freedom, choosing just one coefficient of the allocation vector. And this 1 degree of freedom is sufficient for the trader to choose any path of trade, okay? And then the price which will result in the market is going to be determined by this choice, by this path of trade, okay? And now, recognizing this, we can compute the derivative of price with respect to the changes in the trading flow of an individual trader. So in other words, we can compute the price impact of a trader, okay? And here's a proposition which maps Q and P. So Q describes how allocations are traded, and P describes how the formation of the price. This is a proposition which describes how Q and P, how they map into the price impact of a given trader. And there is some math here, which is nice. You know, I think I should probably do not have time to go into all of it in detail, but basically this proposition says that given any Q and P, the implied price impact of a trader can be inferred through a partial fraction decomposition, which is, you know, interesting because I haven't seen any partial fractions decomposition since doing integration in high school math. But here it comes up again, and it gives the coefficients lambda and tau, this partial fraction decomposition, and coefficient I, and it tells us that for any P and Q, the implied price impact is going to be of the form that there is an instantaneous component of price impact, and there are several exponential components. One of the exponents is with lambda equal to 0. So there are also transient and permanent components of price impact. And here we derive the price impact. It's of the same form as Amgren and Chris, but it's generalized to include also a transient price impact. And ultimately, to close everything, we look for an equilibrium. So we want to start with assumptions of price impacts such that with those price impacts, the implied trading dynamics, they imply the same price impacts that we started with, okay? So this is the consistency requirement. And to put this all together, we have a numerical algorithm to compute equilibrium, okay? So tying everything together, we have a market in which traders, they have inventory shocks. They have quadratic holding costs of holding this inventory. And we have a mechanism for the formation of the price in this market, and for the determination of trades of all traders, how they trade their inventory. And we derive the price impacts of the traders, and we derive the behavior of the price in this market as a function of inventory shocks. This price is going to have momentum, and the equilibrium has to satisfy three sets of conditions. The first one is that individuals, they choose how to trade optimally given the price impacts and given the market price, their expectation about the market price, whether it's going up or it's going down. Markets at each moment of time clear. And the third requirement is that the price impact of every single that enters the optimization problem of every single trader is the actual price impact, which is implied by the behavior of others, by the strategies of others, by the willingness of others to accept the flow of a given trade. Okay, so at this point, let me show some examples, and then I think hopefully I will be able to leave some time for questions at the end. So here is an example which in order to show how the traders trade, I have to we have to look at the matrix Q and vector P. Okay, and the matrix Q tells us for a given vector of inventories what is going to be the vector of flows. Okay, and so here are two examples. One is for a symmetric market where players have symmetric holding costs. And the second example is for an asymmetric market. So different players have different holding costs. Now, what is the interpretation of the holding cost? So a player who has a high holding cost is probably a smaller investor, more risk averse, so more impatient, wants to trade faster. And a player with a low holding cost is somebody who can hold a large inventory and absorb the inventory risk at a relatively lower cost, so a less risk-averse investor. Okay, so the market with different Bs is a market with heterogeneous investors. Some of them are smaller and impatient to trade, and some of them are, large. Okay, and this notion of size here is related to, but it's distinct from another notion of size, which is how much the quantity, the amount of inventory that different traders have to trade. So there's another notion of size, which is not the ability of holding inventory, but the trading needs. So there could be some traders which want to trade a lot, which have large inventories, like brokers, and there could be some traders which don't have very many big trading needs. So here are some of the things that we observe. Okay, so obviously traders with lower holding costs, they can afford to trade slower. So this corresponds to the lower diagonal elements of matrix Q. And traders with high holding costs, they're more impatient to trade, they want to trade faster. Okay. So traders with lower holding costs, they will, and the implication of that is that the market price will be less sensitive. So P is going to have a lower coefficient on the inventory of the traders with lower B who hold their inventories longer. Okay. Then we can also measure the instantaneous price impact. The instantaneous price impact is just the ratio of the diagonal element of Q and the corresponding element of P. So the instantaneous price impact is the ratio of price to flow. And here we see that the large traders have a larger instantaneous price impact than the small traders. And why is that? So the large traders, they're the patient traders. So they trade more slowly in this market. And when other traders identify that there is a large trader in the market, trading slowly, then they know that these are the trades of the large trader, and they know that there's a lot more a lot more trades going to be coming in the future, because this is the type of the trader that's spreading transactions over time, over a long period. And so for that reason, larger traders, they're going to have a bigger price impact. So this is the case because in this model we assume that players can learn instantaneously where any type of flow is coming from, and this is and in practice, of course, players learn where the flow is coming from only gradually, and in fact, high frequency traders, they try to make money by trying to identify the source flow, whether it's an institutional trader trading or not, before everybody else. And that's why so this phenomenon in real market of payment for order flow, that some market makers, they buy the flow of retail investors, and they make money trading the flow of retail investors. This phenomenon of payment of order flow also comes from the fact that they want to learn before everybody else that this particular flow comes from the small retail investors rather than large institutional investors, because this type of a flow is much less persistent and much more like noise traders flow than the flow of large traders. Okay, so here's a solution for a heterogeneous market, a numerical solution with different traders of different sizes. Okay. And in solving for the equilibrium, I was talking about the different kappas, the different trading rates. So these are the eigen values of trading dynamics, and we can also take a look at the eigen vector decomposition, how the different misallocations are traded to efficiency. And something which is interesting, which comes from the properties of these pies, is the sign pattern of the decomposition of eigenvector decomposition. So it turns out that the slowest eigenvector, it's an eigenvector that has a single large trader on one side of the market, selling or buying, and the rest of the market composed of the rest of the traders. And then every single eigenvector breaks the market into two halves. One half are the k largest traders, and the other half is n minus k smallest traders. So that's interesting. So that the some inventory misallocations get traded to efficiency faster than others. And the fastest is when the smallest trader is trading with the rest of the market, and the slowest is when the largest trader is trading with the rest of the market. So that's interesting, but it's also intuitive, because larger traders that have a bigger, that have a lower holding costs are also trading slower. So the summary of the positive results, what we learned from solving the model, is that players with lower holding costs, they trade slower. So a matrix U has lower diagonal elements. Prices are less sensitive to these players' inventories. So that means that in the short run, the price is going to be skewed in the favor of the larger traders. So the larger traders, they spread their orders over time. And by spreading the orders over time, we could say that they exercise market power, because they could coordinate their orders better than the individual retail investors. Together, they do not coordinate their orders. And so the large traders, they're able to get a better price in the short run, and they basically market power and the ability to coordinate orders, gives these traders better trading term. And because of this behavior, how they try to optimize and spread trades over time, their market impact, which I guess is a function of how fast other traders learn that it's really large traders trading, their price impact is going to be larger. And so if high frequency traders make the market closer to our model, so in our model we assume that learning about the source of flow is instantaneous, then high frequency traders would increase the price impact of large traders relative to they would increase the price impact of large traders by front running them, and they would reduce the price impact of small traders. So this phenomenon of payment for order flow, the fact that the retail investors, their orders are separated from others, it turns out this model implies that it's actually good for retail investors because it reduces the price impact of retail investors, and the retail investors get a better execution price. Okay, so so some other things I should mention is that okay, so if we have a market of so one particular interesting case which we can solve in closed form is a market in which there is one single large trader and many small traders, a competitive fringe. So this is an example which we can solve in closed form, and it's good for studying, for example, the distinction between retail investors and institutional investors, because in that case we have a closed form solution. And one of the results that we have here is that the price impact of the large trader has just the instantaneous and the permanent component. And the reason why there is no transient component is that the transient component, if it existed, it would have to come from the heterogeneity among the small traders. So the transient component comes from the following fact in this market: if somebody sells and if the rest of the market, they buy, after they buy, later they trade among each other, and so the selling leads to trading among other traders after the transaction has been completed, and this leads for the price movement after the sales stop. Okay, and so front running is in the title, so I cannot finish without talking about front running. So let me talk about front running. So suppose that we have two large traders in the fringe, and suppose that we start with an allocation in which the first large player has a unit of inventory, wants to sell 1 unit, and the fringe wants to buy 1 unit, and the middle player is sitting at the bliss point, wants to neither buy nor sell. So in that case, the question is, will player 2 just sit at his bliss point at the efficient allocation, or will player 2 want to trade? So will the trade just be among the large trader in the fringe, or will the middle player participate also? So it turns out that with just a large player and the fringe, the price would look like it's shown on this top graph here. The price would have a downward momentum. It would be drifting down. Okay, and the reason why is that the large trader who has a unit to sell has market power relative to the fringe, and so will try to time the sales to trade slower, and this is going to lead to a downward price momentum. Okay, and now when the second large player comes into the picture, he sees that the price has momentum, and he can trade profitably off of this price momentum. So he would want to sell short at the high price and buy back later at the low price. And what this is going to do is that the presence of the middle guy is going to actually change the price path, which is going to be much more efficient. It's going to be closer to efficiency. And effectively what the middle guy do in this market is that he will front run the first large seller. Okay, so front running is, you guys, the large trader starts selling, the second large trader starts selling with him to anticipate the drop in the price and then buy back later at the lower price. And something that this model implies is that here, this behavior of front running is actually good because it brings the market closer to efficiency. In fact, the presence of a front runner encourages the first large trader to trade faster to avoid being front run. And because the market anticipates that the first large player is trading faster, the price impact of the large trader is in fact going to be lower. Okay, so basically that's what's going to happen. So here, front runners actually they improve efficiency. So to conclude, so this is a model where we have a market, trading in the market, where we put together many traders. Their motivation for trade is that they have, some inventories that they want to trade, and they have some holding costs. So we derive properties on the equilibrium path. So how trades lead to price momentum, and how, as a function of the size of the market, players trade faster or they trade slower. And we derive some off equilibrium results. So off equilibrium is the results about the price impact. So price impact is what the price would have been if the player did not trade optimally, but instead deviated and traded differently, and what price this would result. And basically that's the paper. Thank you very much.
Thank you very much, Yuliy. We don't have a whole lot of time, but I think we do have time for maybe one or two brief questions. So if you have a question, just open your mic. Does anybody have a question?
So just one quick question about this last example you showed. Would the middle trader actually sell short and then buy later, or is it just his presence that affects the dynamics of the price?
Yeah, he would actually. Well, it's actually both. So his presence will affect the dynamics of the price. His presence would affect the speed at which the first large trader is selling, because the first large trader, in the presence of this middle guy, he would sell faster. And he will actually, because even so let's take a look what happens. So with the solid price would have been without the middle guy. But with the middle guy, the price goes to efficiency, but it still has the same shape. So of course, given this shape, he would still want to sell short and then buy back later, because that's a profitable thing to do. Yeah.
Good. I think we have time for one more question. okay. I think we're good. Well, Yuliy, thank you very much. It was a pleasure. And if anybody has questions, I'm going to suggest that you write to Yuliy directly, and we're going to end the session. Thank you very much.
Yes, absolutely. Thank you very much for having me, and thank you very much for listening. Yeah.
Thank you, Yuliy.